Hi, I'm Ryan, and I'm a university engineering student. And most of you, probably like me, have seen these videos of the dogs drinking water in slow motion. But I was wondering, how exactly do they do it? So I decided that I would try it myself, and we would figure out how exactly a dog is able to drink water the way they do. So here is a video of me naively trying to drink water like a dog, but as you can see, it is not going very well for me, and I'm not able to really get any of that water in my mouth. It's mostly just splashing out of the cup, and I'm looking like a fool as people walk in and out of the engineering building on campus. So I slowed down that last embarrassing clip of myself in an attempt to analyze what was going on with the water and the reaction with my tongue as it went beneath the surface of the water and came back up towards my mouth. Unfortunately, I wasn't really able to get much out of it. I think the cup was probably a little bit too small, and most of that water was just splashing against the sides and not really coming up towards my mouth. Some problems might be that maybe my tongue is just too small. Dogs usually have a much bigger tongue. They're easier to get down lower into the water and then kind of scoop it back up. But to be sure, we're going to have to probe a little bit deeper to find out the actual mechanisms that dogs and maybe cats use to hydrate themselves this way, because that was just a fail. All I understood was that I'm not able to do it. Fortunately, I'm not the first person to study this, and I have access to other people's research. Here is an article that I found from the Proceedings of the National Academy of Sciences of the United States of America, and the research here is done in collaboration between Virginia Tech and Purdue University student and faculty researchers, and they found some interesting things about the way that dogs drink. Of course, dogs aren't able to drink the way that we do because they have incomplete cheeks and they're not able to suck, so instead they have evolved this lapping mechanism that is shown here. The researchers filmed 19 different dogs with a high-speed camera and then slowed the footage to 1/4 the original speed. Notice here in the next clip that I'm going to show you that the tongues of the dogs that they filmed were plunged into the water at a much slower speed than they were retracted out of the water, and then there's going to be a column formation of the water as it's raised towards the mouth of the dog before the dog actually snaps his jaws shut around the water. She's going to give us her, she can do something with it. She's always been waiting for it with her art, so. Using MATLAB's image processing toolbox and motion tracking programs, the researchers were able to approximate the radius of each tongue that contacts the water. Then, by measuring the movement of the tongue in consecutive frames, the instantaneous velocity and acceleration was calculated for each animal. A similar experiment was performed using glass rods of various diameters. They were plunged just below the surface of water and then retracted at constant accelerations. And you can see in this clip that I'm going to roll right now that there's a really great column formation of water that's pulled up by each of those rods, and then it pinches off there at the very end. After noticing this trend, it was determined that the dogs curl their tongues to increase the contacting surface area and thereby generate a larger column of water. Analysis revealed that there is a relatively high Reynolds number, which is a dimensionless measure of the ratio of steady inertia to viscous drag. Analysis also revealed a high Froude number, which is another unitless ratio from fluid mechanics, and that is the steady inertia over the gravity. After some dimensional analysis of these formulas, the following expression was produced, and you can see from the expression that those things we talked about, the acceleration and the radius there, are the most important factors for this formula that we come up with. Of course, the density and the viscosity, those are going to be constant things for water. So the most important are just the acceleration and the surface area, or the radius of that tongue, as it's withdrawn from the water and forms that column or that pressure difference. I'd like to say thank you to my friend and lab partner Spencer for helping me with the data collection and for the research that went into this. Thank you also to
You're good.
Dr.
Yep.
Richard Rabbit for the wonderful semester and for all that you've taught us about biotransport and fluid mechanics.